The fundamental theorem of arithmetic we know that each composite number has at least one divisor other than 1 and the number itself. We also know that the method of expressing a composite number into product of all possible prime numbers is called prime factorization. In this module, we will learn about the fundamental theorem of arithmetic, which explains how every composite number has a unique prime factorization. The fundamental theorem of arithmetic states that every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. Let's understand this better with the help of an example. Let's take a composite number 105 and factorize it with using factor tree. We divide 105 by 3 and get 35. Then we divide 35 by 5 and get 7. So, the number 105 can be expressed as 105 is equal to 3 multiplied by 5 multiplied by 7. Now again, let's factorize 105. But this time, we will start with 7, so we get 15. Then, we divide 15 by 5 and get 3. Thus, in this case, the factorization can be represented as 105 is equal to 7 multiplied by 5 multiplied by 3. Now, by comparing the two results, we find the prime factors in both the cases are same. That is, both are having the same factors 7, 5 and 3, although the order of the factors has been changed. This is what the fundamental theorem of arithmetic states, that is, every composite number can be expressed or factorized as a product of primes, and this factorization is unique, apart from the order in which the prime factors occur. Now, here's the question. Check whether 25 raised to the power of n can end with the digit 0 for any natural number n. We can solve this question using the fundamental theorem of arithmetic. Let's understand how. If the number 25 raised to the power of n for any n were to end with the digit 0, then it would be divisible by 2. That is, the prime factorization of 25 raised to the power of n would contain the prime 2. This is not possible because 25 raised to the power of n is equal to 5 raised to the power of 2n. So, the only prime in the factorization of 5 raised to the power of 2n is 5. Since the uniqueness of the fundamental theorem of arithmetic guarantees that there are no other primes in the factorization of 25 raised to the power of n. So, there is no natural number n for which 25 raised to the power of n ends with the digit 0. Now let's understand how HCF and LCM of two or more numbers can be found using fundamental theorem of arithmetic. Follow the following steps to calculate HCF and LCM. Step 1. Find prime factorization of the given numbers of which LCM and HCF are required. Step 2. For finding HCF, calculate the product of the smallest power of each common prime factor in the numbers. Step 3. For finding LCM, calculate the product of the greatest power of each prime factor involved in the numbers. Let's take an example to understand this better. Here are two numbers, 32 and 140. We will find their HCF and LCM using prime factorization method. We can write 32 as 2 multiplied by 2 multiplied by 2 multiplied by 2 multiplied by 2, and we can write 140 as 2 multiplied by 2 multiplied by 5 multiplied by 7. HCF is the product of the smallest power of each common prime factor in the numbers. Thus, here HCF is equal to 2 raised to the power of 2 is equal to 4. LCM is the product of the greatest power of each prime factor involved in the numbers. Thus, here LCM is equal to 2 raised to the power of 5 multiplied by 5 multiplied by 7 is equal to 1120. Thus, we have learnt the method of calculating HCF and LCM using fundamental theorem of arithmetic or prime factorization method. Now, in this example, if we calculate the product of HCF and LCM, that is 4 and 1120, we get 4480. And if we calculate the product of the given numbers, that is 32 and 140, we get 4480. We have found that both the values are equal. So, what does it mean? This means that if A and B are two distinct numbers and their HCF is H and LCM is L, then A multiplied by B is equal to H multiplied by L. But this result is not applicable on three numbers. That is, the product of three numbers is not equal to the product of their HCF and LCM. Let's verify this with the help of an example. Here are three numbers, 12, 15 and 18. The HCF of 12, 15 and 18 is found to be 3, while the LCM of 12, 15 and 18 is found to be 180 using prime factorization method. If we take the product of these numbers 12, 15 and 18, we get 3240. And if multiply the HCF and LCM of these two numbers, that is 3 and 180, we get 540. So, from this example, we understand that the product of three numbers is not equal to the product of their HCF and LCM. Now, let's summarize what we have learned. The fundamental theorem of arithmetic states that every composite number can be factorized as a product of primes, and this factorization is unique, apart from the order in which the prime factors occur. HCF is the product of the smallest power of each common prime factor in the numbers. LCM is the product of the greatest power of each prime factor involved in the numbers.